Hi, I'm Gary Harding. I'd like to welcome you to my shop and to our video, Machine Tool Basics. We put together this program to give you an introductory guide to the use of the Smithy AT300, to show you the machine in action and familiarize you with some of the basic tooling that can be used on the lathe, drill press, and milling machine. We're also going to look at a group of measuring tools I think everyone should be familiar with. There's a wide range of cutting techniques that can be done on the AT300. All of them, no matter how complex, can be done efficiently as long as you follow a few simple guidelines. The first and most important thing to remember is that the cutting tools, the drills, lathe tool bits, and milling cutters must be sharp. Second, the cutting tools must be held securely in the machine's tool holders, free from any vibration. Third, the workpiece, or in other words, the metal you intend to cut, must be mounted securely on the machine, able to resist the force of the cutting tools. And the correct cutting speed should be used. These 4 points, tool sharpness, tool holding, work holding, and the speed of the cut, all have a direct effect on the ability of the machine to work efficiently and, in the long run, an effect on the quality of your work. Another factor that will affect your work is the use of a cutting fluid or coolant. The amount of compression and friction that's required to cut metal produces a lot of heat. At high temperatures, the metal being cut will tend to weld itself to the cutting edge of the tool. This effect dulls the tool and leaves a rough surface on the workpiece. The use of a cutting fluid is not mandatory, but for most metals, except for brass and cast iron, it is recommended. Cutting fluid will cool and lubricate. It will prolong the life of the cutting tool, it will allow you to cut at faster speeds, and help to produce parts with a finer finish. As you watch our demonstration, you'll notice that we're not using a lot of cutting fluid. The reason is because we want to get our camera in close to the action. To do that, and to be able to give you a clean picture, we had to cut back on the fluid. I'll talk more about cutting fluid later. Let's start by looking at the lathe. For most lathe operations, the workpiece is rotated by the lathe spindle, and a cutting tool with a single cutting edge is brought against the workpiece to make the cut. In theory, there are only 3 basic types of cuts in all lathe work: turning, facing, and boring. In a turning operation, the tool is moved parallel to the lathe axis to remove material from the outside diameter of the workpiece. In a facing cut, the tool moves at right angles to the lathe axis, removing material on the face or end of a part. A boring cut removes material from the inside diameter of a workpiece. From a practical point of view, that's just the beginning. There are many variations of these 3 basic cuts: drilling, cutting tapers, thread cutting, grinding, and in fact, almost every type of metal cutting operation can be performed on the lathe with the right tools and techniques. I want to show you some of the standard work holding tools that can be used on the Smithy, and then move on to the cutting tools and the controls of the machine. One of the oldest and still most often used work holding techniques is called turning between centers. For this setup, a pair of lathe centers in the headstock and tailstock are used to support the workpiece directly on the lathe axis. The work is center drilled on each end. These center holes act as bearing surfaces for the lathe centers. A lathe dog is mounted at one end of the bar stock and engaged in a driving plate. There are many types of lathe dogs. All are used to transmit driving power of the lathe spindle to the work. Turning between centers has an advantage over using a lathe chuck because it uses the lathe center line as the reference to position and hold the workpiece. Regardless of how many times the work is taken out of the lathe, it can easily be replaced perfectly centered. If a workpiece does not have a center, it can still be turned between centers by pressing it onto a lathe mandrel. Quite often, mandrels are custom made, right in the shop, to turn a workpiece that might be difficult to hold and machine accurately any other way. There are also a number of different types of lathe chucks that can be mounted on the spindle to hold and turn work. The 3-jaw self-centering chuck can be used for most general turning operations where round or hexagonal stock has to be held. All 3 jaws of the chuck work in unison on a scroll system to automatically center the work on the lathe axis. 3-jaw chucks come with 2 sets of jaws. The inside jaws are designed to grip on the inside diameter of a workpiece, by turning the jaws outward. There is also a gripping surface on the innermost portion of the jaws to hold small workpieces. On this 6-inch chuck, if the workpiece has to be held on the outside and its diameter is more than about 2.5 inches, you will have to install the outside gripping jaws. When using a 3-jaw chuck, the ability to accurately center a workpiece depends entirely on the condition of the chuck itself. As the jaws and the internal scroll become worn, the accuracy of the chuck will diminish. The 4-jaw chuck is considered more accurate than the 3-jaw chuck because all 4 jaws can be adjusted independently. This feature gives the machinist the freedom to center a workpiece to any degree of accuracy he desires. It's also more versatile because it can hold square, rectangular, or irregular shaped objects, as well as it can hold round stock. The jaws have inside and outside gripping surfaces and can be reversed in the chuck. This chuck can also be set up to work precisely off-center or bore holes that are not on center. The 4-jaw chuck requires more effort on the part of the machinist to set up and use, but it's a very important work-holding tool that everyone should learn how to use. Both the 3- and 4-jaw chucks use a large chuck key. Never take your hand off the chuck key without removing it from the chuck. If you start the machine with a key in it, it will send it flying. You or someone else in your shop can really get hurt. So make it a habit. Never take your hand off the chuck key without removing it from the chuck. The fastest and most accurate way to chuck small diameter work is to use a collet. There are many different types of collet systems. This one uses a drawbar to pull the collet into a tapered sleeve. As the collet is drawn back and closed, the work is clamped precisely on center. Collets hold very tightly, but have a very short clamping range, so individual collets are needed for each size bar you intend to chuck. A wide variety of turning operations can also be done on a faceplate. The T-slots and holes on the plate's surface can be used to clamp or bolt work directly, or to hold other setup tools like angle plates and clamping jigs. Whatever the setup is, care must be taken to ensure that all of the clamping devices will run clear of the compound, cross-slide, and cutting tool. It is very important that any work installed in the lathe is able to resist the pressure of the cutting tool. A workpiece should always be placed as deep into the jaws as possible in order to give it the most support. As a general rule, if a piece of bar stock extends out from the jaws more than 3 times its diameter, the free end should be given additional support. This can be done by center drilling the end of the workpiece and using a lathe center in the tailstock for support. Here we are using a live center. Rotating live centers can handle higher RPMs for long periods of time because they're equipped with bearings that permit the centering point to rotate with the work. If you are turning pipe or hollow shafts, a bullnose live center can be used in the tailstock to support the end. Another option is to use a steady rest. A steady rest is a work-supporting device that can be clamped anywhere along the ways. It is usually used when drilling, facing, or boring operations have to be done to the end of a long workpiece. 3 adjustable jaws on the steady rest act as bearings to hold work on center. These jaws have to be well lubricated so that they do not mar the surface of the workpiece or cause it to bind. A similar type of device is a follow rest. This tool is attached to the carriage and follows the cutting tool and is used for long, accurate cuts on smaller diameter stock. The 2 adjustable jaws give support to the workpiece on the opposite side of the cut to minimize flex under the pressure of the cutting tool. The selection of a cutting tool, its support, and position in relation to the metal being cut is probably the most important decisions a machinist can make. We're going to cover some of the basics, but I urge everyone that intends to use a lathe to learn as much about cutting tools as possible. They're the key to the quality of your work. Lathe tools are made in many different types of materials, many sizes and styles. The 3 types we're using today are, from the left, high-speed steel, carbide tipped, and on the right, carbide insert. High-speed steel tools can be used for many turning operations on all but the toughest alloys. The tools are sold as blanks in many sizes and grades. The machinist grinds the point of the tool depending on the type of material he is cutting and the type of turning operation he intends to do. A good machinist handbook will give you the standard guidelines for grinding high-speed steel tools. The cutting edge of a carbide-tipped tool is brazed to the end of a steel shank. The shape of the cutting edge, its profile, and cutting angles are manufactured into the tool. A little cleanup on a green silicon carbide wheel and the tool is ready to go. Cemented carbide will handle much more heat than high-speed steel, so carbide tools are able to cut tougher metals and cut at higher speeds. Cemented carbide is also used to make small inserts that are clamped to a tool shank. This style insert is manufactured with a cutting edge on each of its 3 sides. After an edge is dulled, the insert can be unclamped and rotated to the next side. After all the edges have dulled, the insert is thrown away and replaced by a new one. Although this type of cutting tool was designed for the demands of high production work, it's really a great tool for the beginner because it allows even the person with little or no tool sharpening experience the ability to easily maintain a properly formed, sharp tool. No matter what type of material the cutting tool is made of, it's the shape of the tool that determines how it can be used. The profile of the tool's point determines the type of cut the tool is designed to make. The location of the cutting edge on the point of the tool determines the direction in which the tool will cut. Turning and facing tools are either right or left-hand tools, depending on which side of the tool shank the cutting edge has been ground. Right-hand tools cut from right to left because the cutting edge has been ground on the left side of the tool's point. Cutting in this direction towards the headstock is the preferred cutting direction for all turning operations. Facing from the center of a piece to the outer edge, cutting right to left requires a right-hand facing tool. Left-hand turning and facing tools cut from left to right, cutting away from the headstock in a turning operation or from the outer edge to the center in a facing operation. The cutting edge on these tools are ground on the right side of the tool's point. Sending a tool straight into a workpiece in a plunge cut requires a tool that has a cutting edge ground square on the nose of the tool. Here we're using a high-speed steel cut-off blade and holder. Using this style tool to cut a part completely off demands a very rigid setup, even tool feed, and good lubrication. Parting off is usually done at slower cutting speeds than other turning operations and must be done with the work held in a lathe chuck. Parting off cannot be done while the workpiece is held between centers. Boring operations can be done with a high-speed steel tool bit mounted in a boring bar. The bar can be held in a standard tool holder or a specially designed tool holder just for boring. Boring tools have 2 basic profiles, one to bore all the way through the hole, the other to face the bottom of a recess and bore the inside walls, as we are doing here. Boring tools and boring bars come in about as many sizes and styles as there are holes to bore. Here we are using an insert type boring tool. All of these tools require a hole to be drilled first to start the boring operation. Specially form ground high-speed steel tools can be used to cut almost any type of contour. That's a big advantage to high-speed steel tools. They can be ground in the shop to almost any shape. Thread cutting tools are also considered form tools because their cutting edge is ground to conform to a thread profile. The position of the cutting tool in the tool holder is very important. This tool holder can hold 4 tools. In practice, it's a good idea to only load the tools you'll need for the job you're doing at the time. If you use more than one, load the second tool on the opposite side of the holder. Cover the tools not in use to protect your hands. Here I'm using a protective cap that fits over the point. Tools should always be placed as far into the tool holder as possible in order to give the cutting edge adequate support and reduce the possibility of the tool vibrating. In the case of a boring tool, only the length needed to clear the hole should extend out beyond the tool holder. The height of the tool should be set to match the center of the lathe axis. A lathe center placed in the headstock or tailstock can be used as a gauge to set the height. With this tool holder, the tool is raised by placing shims under the tool. The angle at which the cutting edge is presented to the workpiece is also important. For general turning, the cutting edge should have a lead angle in the direction of the cut. For parting off and thread cutting, the tools have to be perfectly square to the work. Here we're using a center gauge to set a thread cutting tool. The tailstock is also used as a tool holder for drilling, reaming, countersinking, and thread tapping operations. Whenever you are installing the drill chuck arbor into the tailstock, remember to screw the plug in the end. The plug will give you the ability to remove the arbor by simply retracting the tailstock spindle. Drills and milling cutters can also be mounted in the headstock. In this case, the chuck arbor is held in position by the spindle taper and a drawbar. This size casting is much too heavy to mount on the faceplate of the lathe, so I've set it up on the cross slide for a line boring operation. The tool bit is held and rotated by the boring bar. The cut is made by moving the casting over the tool's position on the bar with the power feed system. A boring head can also be used for this type of setup. On a precision boring head, a standard boring tool is held in a sliding arm. The size of the hole is adjusted by the tool's outward movement from the center. The graduations on the adjustment screw allow for very accurate finish dimensions. This is the same kind of tool you will later see in the mill spindle. The advantage in this setup is that I'm using the lathe power feed to advance the workpiece. This produces a more uniform finish and it allows me to make deeper bores. In general terms, all lathes will have two basic groups of controls. The controls that govern the spindle speed and the controls that govern the movement of the cutting tool. The speed of the spindle is controlled by adjusting the belts that transmit power from the motor to the headstock. Determining the correct spindle speed in RPMs depends upon the type of metal being cut, the type of material the cutting tool is made of, and the diameter of the workpiece you are cutting. Harder metals, those that are tough to cut, are turned slower than those that are soft and easier to cut. Large diameters are turned slower than small diameters. Charts that outline the recommended cutting speed for various metals can be found in a machinist handbook. To use the charts, match the type of metal you're cutting with the type of material your cutting tool is made of. The charts will then give you the recommended cutting speed for that combination. Cutting speeds are expressed in feet per minute. To convert feet per minute to RPMs, take the cutting speed and multiply it by 4. Then divide that number by the diameter of the piece of metal you are going to cut. Adjust the speed of the lathe spindle to the nearest RPM using the speed chart on the headstock. If you run the lathe at a higher speed, you run the risk of overheating the cutting tool and causing damage to the tool and the workpiece. Running the lathe at a slower speed does not really present any problems. It just takes longer to make the cuts. If you want to run the lathe slower until you feel comfortable with all the controls, that's fine. The movement of the cutting tool is controlled by the carriage assembly and the power feed system. The carriage positions the cutting tool along the ways parallel to the lathe axis. The movement is controlled by the lead screw. The cross slide positions the tool across the lathe ways at a 90-degree angle to the lathe axis. Mounted on top of the cross slide is a compound slide and the tool holder itself. The base of the compound can be rotated to change the angle of the tool's travel. This adjustment has a number of different functions. The most basic is for turning tapers. In a facing operation, the carriage is used to bring the tool to the work. The depth of the cut is set, and the tool is fed across the work by moving the cross slide. In a simple turning or boring operation, the depth of the cut can be set by advancing the cross slide. The carriage is then moved to feed the tool into the work. In a turning cut, the lathe tool cuts an equal amount of material around the circumference of the workpiece. So if the tool is set to a depth of 1/8 of an inch, the diameter of the workpiece will be reduced by a total of 1/4 of an inch. For most turning operations, the machinist will make a few rough cuts to bring the material down within about a 32nd of an inch of the final dimension. Rough cuts are usually heavy cuts with no real concern about the finish on the part. Dimensions are then checked, and the tool is positioned to take the finishing cut. A cut of about 1/4 of an inch is made. and the dimension is checked again. If it's on, the rest of the cut can be made. Turning cuts are generally made by moving the carriage with the power feed system. The gear train that turns the lead screw is driven off the lathe spindle, so the speed at which the tool travels is directly related to the speed of the spindle. Changing the gearing in the power feed system changes the tool's feed rate and allows you to use the lathe to cut threads. The thread chart will show you how to arrange the gears for the thread pitch you want. Thread cutting with this method requires multiple passes with the cutting tool and very accurate working procedures. It's a slow and sometimes tedious process, but for large diameter threads, it's very often the most economical way. Thread cutting is not difficult, but it does take practice. In this situation, cutting fluid is very helpful to cut a clean thread. Here we are simply using a spray bottle, but many other methods can be used to apply the cutting fluid. All are messy, some more than others. Light-duty cutting can be handled effectively with a brush or handheld pressurized can. If you need to cut hard materials or very close tolerances, a mist or full recovery flood system should be used with suitable splash guards, chip tray, and drains. The ability to make accurate measurements is probably the most important skill a machinist can acquire. Precision measuring depends on the accuracy of the measuring tools and the ability of the craftsman making the measurements. The measuring tools I'll be showing will be inch tools. All of them are available with metric calibrations. Some tools, like this 12-inch steel rule, are able to read both systems. One side is in inches, the other side in millimeters. The steel rule is probably the simplest and most familiar measuring tool around, so it's a good place to start. Rules are generally used for making linear measurements directly on flat surfaces or as a standard for setting other instruments that do not have a scale of their own, like this set of dividers. The points of the dividers are set by the rule scale. The measurement is then transferred to the work. Transferring measurement from one instrument to another is a very common practice in metalwork. Rules and the tools that use a rule as their scale, like the rule depth gauge, are only accurate to the smallest graduation a machinist can see and easily read on their scale. That's usually only a 64th of an inch. In machine work, measurements to a 10th or 64th of an inch are considered coarse measurements. Precision measurements accurate to a 1,000th or 10,000th of an inch are beyond the ability of rules. For precision measurements, you have to move to more precise tools like the micrometer. Depth micrometers to measure holes or the length of a shoulder. Inside micrometers to measure the inside diameters of holes or recesses, and micrometer calipers. This is a 1-inch mic capable of measuring outside diameters or thicknesses up to 1 inch, with an accuracy to 1/10,000th of an inch. With a micrometer, the measurements are made by placing an object in contact with the instrument's fixed anvil and adjustable spindle. The dimensions are then calculated by adding the readings off of the mic's 3 scales: the barrel scale, revolving thimble scale, and the vernier scale engraved on top of the barrel. The measuring range of a micrometer head is limited to 1 inch. Larger mics use the same head mounted to a larger frame. This 2-inch mic has a measuring range from 1 inch to 2 inches. A 3-inch can measure from 2 inches to 3 inches. To measure dimensions from 0 to 3 inches requires a set of 3 mics. You can make inside measurements with a set of outside mics by using a variety of tools and techniques that transfer the dimension from the object being measured to the micrometer. Here I'm using a telescoping gauge. The head of this gauge has 2 spring-loaded plungers that expand across the inside wall of a cylinder. The plungers are then locked and the gauge is transferred to a micrometer. The dimension of the hole is determined by measuring across the gauge. The range of an individual telescoping gauge is limited, so they usually come in sets. This set is able to read from 6 inches down to 5/16ths of an inch. For smaller holes, you can use a set of small hole gauges. The tips of these tools expand as the adjusting knob is turned. Once in the hole or recess, the tip is expanded to make contact with the inside walls. Again, the gauge is transferred to a mic to make the reading. A set of adjustable parallels can also be used to gauge the width of slots by expanding and locking the parallel against the inside walls, then measuring the parallel with a mic. Precision calipers like the 6-inch dial caliper are popular alternatives to micrometers because they can make inside and outside measurements and have a much greater measuring range in a single tool. The dial also makes this instrument very fast and easy to read. The stationary beam of the caliper has a scale that's graduated in inches and tenths of an inch. These readings are then combined with the reading off the dial that's mounted on the sliding jaw. This dial is graduated in thousandths of an inch. Dial calipers also have a rod to give the instrument the ability to make depth measurements. A depth base attachment can be installed on the end of the beam to help with larger holes. Both the caliper and the micrometer are available in models that have electronic readouts. These tools combine traditional toolmaker's craftsmanship with computer logic to give readings down to 1/2 of 100,000ths of an inch. I usually don't need to read to 1/2 of 100,000ths of an inch, but I do like these instruments because they're one of the only precision hand tools capable in reading in inches or, with the push of a button, in millimeters. They also have a function that allows you to zero the reading anywhere along the measuring range of the instrument. You can set the dimension you want, let's say 1.5 inches, then zero that point. Now any movement of the slide will give you a reading of how far over or under the 1.5 inch mark you are. Now let's look at a group of tools that's used to determine angles, starting with the steel square. This is a precision tool used in layout, machine setups, and inspection work. It's made in a variety of sizes, and it's used whenever a true 90-degree reference is needed. Another square that is a must in every shop is a combination square set. The complete set is made up of a heavy graduated steel blade, a combination square, and 45-degree miter head, a protractor head, and a center head. The center head is used to find the center of a square or round stock, so important to lathe work. The combination square head gives you a 90 and 45-degree reference, and because the blade is graduated and adjustable, can be used to make linear and depth measurements. The protractor head goes one step further to give the ability to gauge angles from 0 to 180 degrees. A variety of other protractors can be used depending upon the type of work you are doing and the accuracy you need. The advantage of the square head protractor is that any side of the head can be used as a vertical or horizontal reference line. Accuracy is to 1 degree. No matter what kind of drilling, turning, or milling operation you have to do, you cannot expect to make precision cuts unless all the machine components are aligned and the workpiece is positioned correctly on the machine. I've saved these two tools for last, the dial test indicator and the dial indicator, because these are the tools that will help you measure and gauge the movement of your machine and workpiece. Indicators with balanced dials, dials with the same progression of numbers on either side of the 0 mark, will not only tell you the amount, but also the direction of any misalignment. This is the kind of tool that is used to center work in a 4-jaw chuck, or check the position of work set up on a milling table. The measuring range of this indicator is only 1/1000th of an inch overall. When you're making these kind of adjustments, that's all you'll need. Indicators with a measuring range of 1 inch or more have continuous reading dials. Graduations are in thousandths of an inch, with each revolution of the dial equaling 1/10th of an inch. This type of indicator is used to precisely gauge larger movements, like the movement of the carriage or cross slide, and the offset of the tailstock for taper turning. The other measuring tools that help the machinist gauge the movement of the machine are the graduated collars and scales on the machine itself. All the graduated collars on a Smithy are floating, which means that they can be zeroed at any time to give you a recognizable starting or stopping mark. The tailstock also has non-adjusting linear scales along the barrel to help gauge the depth of drilling tools. Remember that the collar on the compound hand wheel only gauges the movement of the compound slide and the lathe tool in a taper cutting operation. If you want to use the compound's collar to accurately gauge the depth of the cutting tool for your turning operation, the compound has to be set at a true 90 degrees. To gauge the tool depth for a facing cut, the base of the compound slide has to be set at 0. If you have the compound set at an angle other than 0 or 90, you cannot use the compound calibrations to gauge the depth of your cuts because you have in effect set up a triangle. You can use this principle to your advantage if you set the compound at 30 degrees, because at 30 degrees the value of the graduations is reduced to 1/1000th of an inch. This will allow you to make finer adjustments. The tricky part to using calibrations accurately will be your ability to work with the machine's backlash. It is this play when you change from one direction to the other with no corresponding movement to the table that's called backlash. All machine tools have it to some degree, and it will throw off your calculations if you don't learn to work with it. The thing to remember is to always make your calibrations by turning the hand wheel in the same direction. In other words, if you start at 0 and advance across slide 3 revolutions of the dial, and you want to return to your start mark, you have to turn the hand wheel back 3 turns to the 0 mark, then continue for 1 more turn. Reverse directions, taking out the play and the feed screw, and come back to the 0 mark in the same direction as your original movement. Understanding how these scales work and learning how to use them in conjunction with hand measuring tools is the first step in gaining complete control over your machine tools and the accuracy of your work. If the project you're doing needs to be grooved, keyed, slotted, drilled, or just machined flat, the tool you need to turn to is a mill drill machine. For milling operations, the workpiece is held on a sliding table and fed into a revolving cutting tool. The shape of the cut is governed by the profile of the milling cutter and the controlled movement of the machine's table. Here is a part that was made on a vertical milling machine. The finished shape is complex, but each individual cut that went into producing this part was very simple. That's really the key to milling, taking each cut one step at a time. A good machinist will look at a design and think of it as a progression of simple milling and drilling operations. This part required 22 separate cutting operations, 5 different milling cutters, 4 drills, 5 different types of work holding tools, and a total of 9 individual setups on the milling table. Each setup was carefully planned in advance, so as the cutting progressed, the machinist did not lose the ability to hold the part rigidly. A successful milling operation requires a careful choice of cutting tools, work holding devices, and table movements. The most widely used cutting tools on a vertical milling machine are the end mills. These mills have cutting teeth on the sides and bottom, so they can be used for any combination of planing and facing cuts. Solid end mills are made from a single piece of cutting material and can be either single end mills with a cutting edge ground on one end only, or double end mills with a cutter on both ends of the shank. For general machining, end mills are ground with either 2 or 4 cutting edges. For high precision cuts with fine finish, tools with 6 or more cutting edges are available. 2 fluted mills are good for machining soft materials like aluminum and brass. Both cutting edges meet in the center of the tool, making these tools center cutting. This means the mills can be plunged into the workpiece like a drill, then moved in any direction to the side. 4 fluted end mills are better finishing cutters because they have a greater number of cutting edges and are generally more rigid than 2 fluted mills. Only center cutting 4 fluted mills can do plunge cuts. Here are 2 4-flute mills. The one on the left is center cutting because 2 of its 4 cutting edges meet in the center of the mill. The one on the right is a non-center cutting mill. Other special purpose mills, like ball end mills, dovetail cutters, corner rounding cutters, T-slot cutters, and keyway cutters, are available for cutting specific shapes on a vertical milling machine. If you're doing a broad-facing operation, it's always better to use a large milling cutter, as large as the machine and setup can handle. Shell end mills start at 1.25 inches in diameter and are an excellent facing tool. They differ from solid end mills because the mill and the shank are separate. With this system, different size mills can be used on the same arbor. Small face milling cutters can also be used. This one has a 2-inch cutting diameter and uses 3 replaceable carbide inserts, similar to the ones we used on the lathe. Fly cutters use a single-point cutting tool to plane flat surfaces. The tool bit is mounted in a groove on the cutter's head. As the spindle turns, the point of the tool cuts a circular pattern on the workpiece, producing a flat surface. Fly cutters are able to take fairly wide, light cuts which produce an excellent finish. They're economical and easy to maintain. Slitting saws can be used for cutting narrow slots or just cutting metal in two. They come in a number of widths, diameters, and tooth sizes. The 3-inch diameter size is a good general-purpose saw for the equipment we are using. The teeth on these tools are very fine compared to other milling cutters, so the cutting speed should be slow. Hole milling operations are another important job that can be done on a smithy. The most commonly used tool for this work is, of course, the drill. But after the hole is drilled, other operations can follow to modify or finish the hole. There are many different types of drills. Today we are using the type most commonly found in the shop, the Chisel Point high-speed steel twist drill. These drills are called chisel points because the two cutting edges do not meet at the center of the drill. So the point, the part of the drill that makes first contact with the metal, does not do any cutting. That's why these drills walk around on the surface of a part unless they are given a good punch mark or a starter hole. Drills over 1/2 inch cut much more efficiently if a pilot hole is drilled first to take the pressure off the point of the tool and allows the cutting edge to lead the way. The size of the pilot hole should be as wide as the chisel point on the drill. Chisel point drills generally produce a hole that's a few thousandths of an inch over the drill size. That's okay for a bolt or screw hole application. But if a hole with a higher quality finish and accuracy is required, then you must go to a reaming or a boring operation. Reamers are multi-cutting edge tools used to enlarge a hole to an exact size and smooth finish. In practice, you start by drilling a hole slightly smaller than the finished hole size and follow with a reamer of the exact hole size. Reamers are very fast and economical in small sizes. If you don't have a reamer of the exact size, a boring operation can be used to bring a hole to an exact dimension and fine finish. Here we are using a precision boring head and a carbide cutting tool. With a rigid setup and even feed, this type of tool can machine very accurate holes from 1/2 inch up to 4 inches. Countersinks and counterbores are both used to enlarge, reshape, and finish the top of a drilled hole. A countersink campers the top of a hole so that a flathead machine screw can be set flush with the surface. Counterbores cut perfectly flat-bottomed holes in order to set philistor or socket head screws below the surface. They can also be used to mill a flat seat on the surface of a casting for nuts and bolts. This operation is called spot facing. All counterbores and some countersinks have non-cutting pilots to help position a tool correctly over the hole and to prevent the tool from vibrating or chattering. Chattering would cause an uneven surface and a poor screw seat. Center drills are a combination drill and countersink. Besides being used to drill center holes in bar stock that will be held in a lathe using lathe centers, they are also used to make starter holes for drills. Tapping screw threads on a drill press requires the use of a specially designed tapping head and machine taps. Hand taps should never be used on a drill press under power, but you can use a drill press to start the threads and assist in alignment. This is a spindle from the Smithy AT300 mill drill head. The spindle has a Morris taper number 3. Any MT3 tapered shank tool can be installed in the spindle, but we recommend that for all milling and drilling operations that the tools and tool arbors be secured with the use of a drawbar. We have been using a number of different end mill holding tools. This one is a precision end mill adapter. The end mill fits into a hole in the tip of the adapter and is held in place with a set screw that tightens down against the driving flat on the mill shank. Collets are also a good choice for holding end mills because of their natural ability to accurately center the objects they are holding. I prefer spring collets in this special holder because the collets are fast and easy to change. Morris taper number 3 collets can also be used to hold end mills. The drawbar is used to pull the collet into the spindle taper and close tight on the end mill shank. Straight shank drills and reamers are held in a drill chuck. Chucks are mounted on arbors and installed in the spindle with the drawbar. Chucks should be hand tightened and checked to make sure the tool is centered properly. Then tighten progressively around the chuck with the chuck key. On keyless chucks, the jaws are opened and closed by hand. Keyless chucks are fast to use, but are generally limited to light and medium duty drilling. The selection of a work-holding tool or technique is as important as the selection of the cutting tool. If there is a failure in a milling or drilling operation, 9 chances out of 10, the failure was due to either the work being pushed out of the original position by the force of the cutting tool or the work flexed because it was not properly supported. All of the work-holding tools and machine attachments that are installed on the milling table are held in position with the help of the table's T-slots. It is important that the table and the T-slots be kept clean and free from any burrs, nicks, or rust. A machine vise is by far the easiest way to hold small workpieces for milling and drilling operations. On all vices, the fixed jaw is always used as a reference to position the vise squarely on the milling table. The movable jaw on a vise will tend to lift the work as it tightens. To prevent this, a soft face hammer is used to tap the workpiece as the jaw is turned tight so that the workpiece remains seated properly. This type of precision ground screwless vise is designed to pull the movable jaw down as it tightens on the work. This makes it much easier to set and clamp the work square with the table. The workpiece should be set as deep into the jaws as possible. If the work has to be high on the jaws to give clearance for machining, it should have full support. Here we're using a set of parallels to raise the work and provide support against the downward force of the cutting tool. If you're drilling all the way through an object, the parallels can also be used to give enough clearance under the workpiece so that the drill can exit the hole without touching the vise. Adjustable vices are helpful in holding parts that have to be machined at an angle. Even though a vise may have a scale made into the vise, always double-check the part in its setup with a measuring device to confirm the angle is accurate. Work that is mounted directly on the milling table can be held in place with T-nuts, threaded studs, and strap clamps. The strap clamp should always be parallel to the table, with the stud and nut as close to the work as possible. The outer end of this clamp is being supported with a step block. There are many other types of tools used in conjunction with strap clamps for supporting work. V-blocks can be used to support round stock or other shapes of material mounted directly on the milling table or in the jaws of a vise. Slotted angle plates are used in setups when the piece being machined needs to be held at a 90-degree angle to the table. These plates are heavy and are made in a number of sizes. The work can be clamped or bolted onto the angle plate. An adjustable angle plate is used to hold work that has to be milled at an angle other than 90 degrees. This tool can hold work flat or at any angle to the left or right up to 45 degrees. It is very useful for holding thin plates, castings, or other parts that might be difficult to hold and totally support in a vise. The Smithy step block can be used for a number of milling and lathe operations. Here we are using it to bring a workpiece closer to the milling spindle. Work can also be mounted on the side as you would with an angle plate. An auxiliary cross-slide table can also be installed on the Smithy's milling table. There are some applications where this can increase the versatility of the machine. Milling in an arc requires a tool that will hold and precisely turn a workpiece. The tool used for this type of machining is the rotary table. Graduations around the table's circumference and on the hand wheel allow the operator to manually adjust the location of the workpiece anywhere within the 360-degree movement of the table. The rotary table is an extremely versatile tool that can be used to mill complex angles and patterns, as well as indexing operations. It is also used extensively to drill accurate hole circles. Cutting gears is another indexing operation that requires a tool to help the machinist accurately divide a circle into an equal number of parts. Here we are using a universal dividing head. After each gear tooth is cut, the machinist turns the handle to reposition the gear blank for the next cut. The indexing plate behind the control handle is a very simple programming device. It uses a series of precisely drilled holes to divide a circle into a predetermined number of parts. After the machinist calculates the number of teeth needed in the gear, he uses the holes in the indexing plate as guides to make the cuts. A less elaborate device to do the same type of work is a spin index. The indexing plate on this tool only has 36 holes, one every 10 degrees. and a vernier hole system along the top to find the 1st through 9th degrees. It's a neat system that can index in 1-degree increments. There is also a degree scale on the outer portion of the plate to help you keep track of where you are. It's not as fast and versatile as a universal dividing head, but it gets the job done. The controls for the mill drill head are fairly simple. The head can be raised or lowered by turning the mill head extension lever and locking into position with the locking handle. In the center of the drill press handle is a micro feed clutch. When this knob is pressed all the way in, the drill press handle is disengaged and the fine feed mechanism is engaged. The quill lock is turned away from the head to lock the quill. The milling head has 12 spindle speeds, from 125 RPMs to 1600 RPMs. The speeds are adjusted by shifting the belts on the milling head and the main drive system. It's always easier to adjust the belts with the drive clutch in neutral. Determining the proper spindle speed for milling and drilling depends on a number of variables: the type and size of the cutting tool, the material you're cutting, the use of cutting fluid, and especially the rigidity of the setup. All have to be considered. Just as in lathe work, begin with the recommended cutting speed based on the type of metal you are cutting and the material the cutting tool is made of. For drilling, a machinist handbook will have charts that use the cutting speed as a guide to find the correct spindle speed in RPMs based on the diameter of the drill you are using. With a hand feed, the machinist has to watch and feel the progress of the tool. You should be looking for even chips as the drill goes into the work. When you're working with very small drills, you lose the ability to feel the drill. That's when you should install a micro drill adapter. This adapter can be mounted in a larger drill chuck or, for better accuracy, in a collet. It gives you a very sensitive feel and is really the best way to get the job done when working with bits from number 50 through 80. Remember that the flutes of a drill are designed to carry the chips up and out of the hole. As the hole goes deeper, the possibility of the chips clogging the flutes and causing the drill to bind increases. This is especially true with small drills. Using cutting fluid and frequently removing the drill to clear the flutes can prevent the drill from jamming in the hole and breaking. In milling, the diameter of the cutter and number of cutter edges on the tool are used to calculate the speed of the spindle. The depth of the cut and the feed rate go hand in hand on a milling machine. My suggestion with end mills is to start rough cuts with a conservative depth and modest even feed rate. You can always increase the depth of the cut and feed as you see that the cutter and setup are working out. On machines with manual feed, you will be able to feel the pressure of the cut. Finish cuts will always be slower feeds and shallower cuts in order to get a good finish. Most standard end mills are right-hand cutters, meaning that they cut when they are rotated clockwise over the workpiece. Feeding the work into the mill against the rotation of the tool is called up milling. This is the recommended feed direction for milling on the Smithy. For light cuts, you can apply cutting fluid with a spray bottle or brush. For heavier cuts, a constant flow is best. Direct the fluid on the cutting tool so that it can carry away the small chips that accumulate in the flutes and around the tool. Safety guards and a good recovery system are necessary. Before I close, I'd like to go through some of the maintenance procedures for the AT300. It's very important to routinely clean, lubricate, and adjust the machine in order to maintain its accuracy and efficiency. Operating the machine in a safe and clean work environment is the first step in preventing accidental damage. I can't emphasize enough how important it is to check and double-check your work setups before you turn the machine on. The jaws of the chuck slamming into the cross slide or the compound can cause a lot of damage to the machine. The workbench that you use to support the machine is very important. A good vibration-free level table will improve the quality of your work and increase the life of the machine. Never under any circumstances mount the Smithy on a bench that is shorter than the lathe bed. The ways are not a shelf for your hand tools. Keep your tools off the lathe, on another table, or on a shelf under the lathe. Don't put tools on a shelf above the lathe where they can vibrate off and fall into the spinning lathe. Always clean away the metal chips as the work progresses. but never with your bare hands. Pay special attention to the spindle tapers. The spindle socket should be inspected and cleaned with a soft cotton cloth every time you change tools. The way wipe on the carriage should be cleaned and replaced as soon as they are worn. You can cut new wipes from rubber, leather, or felt and install them whenever necessary. The lead screw can be cleaned with a stiff bristle brush. Chips will find their way into the lathe chuck, and if not removed, will accelerate wear and reduce accuracy. Remove the jaws and clean the chucks frequently. A good shop vac makes simple work of small chips. I do not recommend blowing the chips away with a compressed air hose. It's dangerous, and it just forces chips and trash into areas of the machine, increasing wear. Special precautions should be taken for dusty materials like wood and plastics, because the dust will cling to the machine's lubrication. Cast iron is very dirty, and the dust is very abrasive. If I'm working with cast iron, I usually try to cover as much of the machine that is safe to cover. Completely clean the machine after each workday and wipe the unpainted surfaces with oil to prevent rust. Lubricating the machine should be as routine as turning the motor off and on. It should be the first thing you do when you begin a day's work and the last thing you do after you have cleaned up at the end of the day. The machine is equipped with oil nipples to lubricate the bearings and the ways. The chart in the owner's manual will give you all locations. A 10-weight oil should be used on the bearings and in the headstock. The sight glass for the headstock oil level is located under the chuck. The fill port is on the back of the headstock. The correct level is halfway on the sight glass. It is very easy to overfill the headstock. Only pour in an ounce at a time and wait to see the results in the sight glass. Always oil the lead screw and ways at the start of the work day. The clutch on the main drive spindle does not require lubrication. The clamping levers on the machine are all designed to apply satisfactory clamping force with your hands. Do not use a pipe or any other tool to get additional leverage. Routinely check to make sure the lever handles are tight. All of the ways on the Smithy have adjustable gibs to compensate for wear and maintain the proper fit between the sliding surfaces. The adjustment of the gibs affects the rigidity of the cutting tool and the ability of the machine to make accurate cuts. There are a few points I'd like to emphasize. First, it's important to understand that the locks for the compound rest, cross slide, carriage, and tailstock all act directly on the gibs for their locking power. When you adjust the gibs, make sure the locks are backed off completely. As the gibs tighten, the effort it takes to turn the hand wheel increases. Each machinist will adjust this movement according to the work he is doing, his experience, and personal preference. The important thing to remember is that gibs should be adjusted evenly. On the cross slide, the effort it takes to move the table should be the same throughout the entire length of the table travel. If the hand wheel begins to turn easier as the cross slide approaches the end of the travel, the gibs are not adjusted evenly. Make all of the adjustments to the cross slide gib with the table centered on the carriage. Back off the set screws and jam nuts and start your adjustments with the inside set screws. Set the tension you want, then adjust the outer screws to match. If you seem to feel more hand wheel resistance in one direction than the other, the gibs are uneven. If there is more resistance going away from you, the leading edge of the gib is too tight. Back off the set screw just a bit. If there is more resistance coming towards you, adjust this one. When everything is set, carefully lock the jam nuts. I usually adjust the compound gib tighter than the others, and unless I'm using it to cut a taper, I leave the lock on tight. The carriage has 2 gib screws. Again, feel for even hand wheel resistance in both directions. As you work with the adjustments, you will feel the difference even gib tension will make on the hand wheel. The tailstock also has a gib. I usually adjust the tailstock gib freer than all the others so that it's easier to position. Again, the lock acts on the gibs and automatically brings the tailstock into alignment when it's tight. The most important adjustment on the lathe is the alignment between the tailstock spindle and the headstock spindle. For normal turning, these 2 points must be perfectly aligned. Checking and adjusting the alignment requires the help of a measuring tool, like this dial indicator. If you do not own a dial indicator, do not attempt to adjust the tailstock. I'll put that another way. If you don't have one of these, don't loosen these bolts. The alignment has been set at the factory. The offset gauge on the back of the tailstock is only to be used as a guide for approximate placement. A simple test to check alignment is to set up a piece of bar stock to turn between centers. Take a cut about 7 inches long, then measure the diameter at both ends of the cut. The dimensions should be exactly the same. If they're not, do the next test. Prepare a piece of bar stock about 16 inches long to turn between centers. Make a few undercuts at either end and in the middle, as you see here. Next, set and lock the cutting tool to take a light finishing cut across the two shoulders. Don't touch or adjust the tool. Just let it run past the undercut to the next shoulder. The diameter of the shoulders should be the same. If they are not the same, adjust the tailstock offset by 1/1000th of an inch using the indicator. Lock up the tailstock adjustment and run the cutting test again. Keep repeating the process until the two shoulders are the exact same diameter. When you finish, put the bar in your toolbox, because now the next time when you want to reposition the tailstock dead on center, you can use the test bar and an indicator to make the adjustments. Let's move on to the drive system. Always keep the drive belt covers in place when the machine is in operation. This keeps you safe from the belts and gears and keeps foreign objects out of the drive system. Metal chips may still find their way into the belt covers, so it's a good idea to clean these out as soon as you notice them. Pay close attention to the area around the hanging wheel assembly. The best way to clean this area is to remove all the gears and components except for the primary drive gear. Clean the gears and lubricate the system as you reinstall it. Make sure the hanging wheel gears are fully meshed and the tension slide set screw is tight. If it is loose, the weight of the gears will always cause the tension slide to drop down. For maximum performance, always keep the belt snug. By loosening the nut on the back of the gearbox, the middle pulley can be moved to adjust the belt tension. A second adjusting point is located between the motor and the machine base to tighten or loosen the motor pulley. The belt drive for the milling head has two positions. Belts that come with the Smithy do not require the use of the tensioner. If a substitute belt is used, the tensioner is helpful in compensating for any possible variations. The tensioner can be adjusted by loosening the tension roller and repositioning it along the tension arm. The electrical system of the Smithy is very simple and should not require any maintenance. The switch is a motor reversing switch with an off position in the center. Always let the motor come to a complete stop before reversing directions. The motor should be connected to a well-grounded 30-amp circuit. As a safety precaution, always disconnect the machine from the power source when not in use. This will prevent anyone that's not familiar with the machine from accidentally starting the motor. If you have any problems with the motor, have it checked by a qualified electrician or call a Smithy service technician for advice. The biggest enemy of any machine tool is rust, especially if you live in a very humid climate. The best protection from rust is to keep the machine clean and coated with an oil that drives out moisture. If you're going to store the machine with a cover over it, be sure that the cover is ventilated. Before you start to use your new AT300, I recommend that you read the operator's manual from front to back and get to know the machine thoroughly. It's very important to know your tools, understand the tool's operating limits and safety precautions. There are also a number of reference books on the market that will give you detailed information on machining operations. Our catalog has a good selection. You know, some people think that it's easy to learn how to use machine tools. Others might tell you it takes a lifetime to master these tools. Both statements are probably a bit exaggerated. My experience has taught me that when you start working with these machines, you'll learn something new every day. I hope this video has given you a good start.